So welcome to another class about the Branches spaces. And today we'll be doing let's just say the complement of, not complement, finalizing, let's say, theorem 8, which was about factoring a Blasicki product out of a bounded type function. In this one, we would characterize the functions of bounded type by a certain expression. And this is the result. This will be the main theorem of today. So let F be analytic. And say that F of Z is, let's say, different than 0 in a certain neighborhood of the origin. In other words, the origin is not an accumulation point, accumulation of the zeros of F. Then F is a function of bounded type in the upper half plane. Oops. If and only if it has a certain representation. The Blasicki product, which we know that it already converges by theorem 8, times a function E, a function with no zeros, and that function with no zeros you can write as an explanation of the difference. And we know that the real part of dj, j is greater or equal than 0, j equals 1, 2. Greater or equal than 0 in the upper half plane, of course. Okay, so before I prove that's the Nevalinna's factorization, let me write in the way the Branges write in the book. Okay, so how he does it. So we know that J having a no negative real part, we know by Poisson's representation that it has a specific form, which is, let me write it explicitly. So that was Poisson's representation of the function, and we know that these numbers P and Cj, they are real, and Pj is non-negative. Okay. So in particular, if you just take the real part, which is usually what we do, have just Pjy, and then the convolution with the Poisson kernel. Great. So what the Branges do is the following. Let me take my notes. Where is it? Yeah. He defines H to be. And I have to be careful now, so I get the same H. I'm writing as G1 minus G2, so I guess the H should be P2 minus P1. And then he writes G as just the difference of, let's say, G1 minus G2, but without the P's. So that would be just the C1 minus C2 plus 1 over pi I. And then sigma 1 minus sigma 2. And this sigma 1 minus sigma 2 is what we call mu. Okay. And then he claims something. He claims that, well, so mu will be what? Mu will be what's called a function of bounded variation, a locally bounded variation at least. And he defines what it is, the variation of that thing, but only if you integrate when you're dividing by 1 plus t squared. Okay, so what he does is that he defines, he says something. He says that, well, then this thing is finite. Okay, and this thing here is defined as the sup over all partitions of tk minus. Partitions would be, since you take on the real line as a whole, then you just take a sequence of points in the real line, increasing sequence, let's say. Okay. And then you can easily show that this is finite because a simple computation will show that this is indeed less or equal than just integrate, just apply the triangle inequality here in the definition of the sums. Okay, and then he goes to say that, well, but the opposite is also true, and that's the content of conversely. That's the content of a lemma tree on page 22. So the branch shows that whenever we have some function mu on the real line, so that let me say this star here, that computation here. So that star is finite, then you can always write as a difference. Let me write this different symbol. Let's say nu1 minus nu2, where nu_j is non-decreasing, and for each one, star holds. So star is finite for each nu_j. Okay, that's what he did. So alternatively, you could say that, and that's the way he writes it, that F is a Blasek product, then an E to I H Z, because that would be G1 minus G2. And the way I'm writing with a minus here. So it should be P2 minus P1, dH, so that's correct. And then times a certain function, and then times a certain function E to the G, the way I defined before, such that the real part of G equals just a y over pi integral of 1 plus t, integral of the mu t minus x squared plus y squared. And star is finite. Okay, so that's the way he writes it. And and because of that, he needs this lemma 3, which I won't show. And so you could go in the book and read it. The way I'm going to prove theorem 8, the way I write here, which is much simpler and direct. And another comment is that, well, if mu in this converse part, if mu is, let's say, C1, it could be just absolutely continuous, but let's say C1, then the mu t is just this measure here, which is the measure that I'm using here in this definition, is exactly just mu, the moduli of the derivative, let's say dx. I'm using t, so let's keep using t. Okay, this is another remark. Okay, any questions here? Okay, great. So let's start proving this. So proof. So what's the thing? It's a very fast proof if we don't do this lemma about the measures and etc. So by theorem 8, we know that the Blaschke product is convergent where Zn, these are the zeros of F. And we know that F is just some B times L. Okay, and L is still a function of bounded type. That's what we proved in theorem 8. Actually, we proved that if F is Q over Q, and then Q times F is bounded by M, then the same bound holds for L. And that's something we're gonna use later on in another result, but it's something to keep in mind. Okay, so, and then L is bounded type, and moreover, N has no zeros. Okay, now we can use problem 24. So then by problem 24, I can write L as P over Q, both bounded by 1. Let's see if that's the way I'm writing it. Yes, P over Q, both bounded by 1. And P and Q with no zeros. This actually holds for every L. It doesn't need to not have zeros. For any function of bounded type, you can write it like this. This is the problem 24. Okay. So the tricky part of showing problem 24 is removing the zeros of Q. But in any case, since Q has no zeros, then P has no zeros because L has no zeros. So therefore, I can definitely write P, let's say P as E to minus G1. What's the best way? Did I write it? Oh, I wrote it as G1 minus G2. So it should be, to keep the notation, G2, and let's say Q equals E minus G1. So P over Q would be G1 minus G2. And then we know that, and since P and Q are moduli less or equal than 1, that's exactly the same as saying that the real part of Gj is greater or equal than 0. Okay, so that shows that if it is a bounded type, then it has this form. Or equivalently, by the Branges remark on this measure things, it has also is the same as having this form here. Okay, so then now we need to prove the converse, and the converse is obvious. And that finishes the proof. Why the converse is obvious? Because, well, if it has this form, this is bounded by 1, and this is definitely the quotient of two things that are bounded by 1. So it is of bounded type. Okay, so it's very simple result stemming from theorem 8. And we just need this, if you want the Branges form, then we just need this remark, this additional comment about these measures. Okay, any questions here?
Yeah, I've got a question.
Yep.
So when you define P and Q, you define it as the exponential of this. Oh, sorry. You want to define G1 and G2.
Yes.
So it would be like the logarithm of P and Q.
Yeah.
But I mean, it's like it's a complex logarithm, right?
Yes.
And how are we sure that this thing works out? Because I mean, the complex logarithm is always a bit tricky. So
yeah, so it's always to keep in mind one thing: whenever you have a function which has no zeros, and that's the case of P and Q, you can write it as an exponential of something.
Okay, okay, that's good.
That's again one of these. I'm assuming that everybody has at least a little background in on the basics of complex analysis. Yeah, and I think this exponential thing I did in my undergraduate students. It was not even the master. So when it's something that's too technical, then I explain like these things with the measures, etc.
Yeah.
And I go over it. But this thing is really standard. If you
okay,
taking logs of some things that the other things that only doesn't vanish at a certain, let's say, disk, etc. But it has zeros in other places, and I have to be careful with certain things. And okay, then I will explain how we do it. But here it's fairly simple.
Okay.
So the result that I'm invoking here is whenever you have a function which doesn't have a zero, is in an open connected domain, then you can write it as an exponential of something else.
Okay, great. Thank you.
But it seems that you are the only one that asks questions, which I like, but nobody else asks questions. Maybe if you don't have any questions, then you can just make a remark. That would be also good. Great. So let's go to what? Let's go to theorem 10. So theorem 10 on the page. This is the hint. This is a comment we just did. Okay. So this number here, h, it turns out to be important for the definition of the Branges spaces. So the Branges spaces will be certain functions that has a certain finite L2 norm with respect to some weight on the line, and this will be entire functions. And in every case like this space will not be complete if you don't put an additional decay condition at infinity. As we know, the complex plane is like mapped to the unit sphere, and there's always a problem with the North Pole. Let's say if you map it in the way that I'm thinking of. Anyway, so there is always conditions at infinity. And this mean type, which we call mean type, would be this number h. And that would be the condition at infinity, related with this condition at infinity that I'm mentioning. So it would be nice to have some formulas for it. And that's the content of theorem 10. Select, let's say f be a function of bounded type. And again, and the zeros of f don't accumulate. Okay. Then in the factorization, f equals b e to I h z and e to the g. Let's see, factorization. Let me put, let's see, factorization n for Nevalinna. The n factorization. We have two formulas for h. H is the limit sup when I goes to infinity of log divided by y, but h is also 2 pi lim when r goes to infinity of 1 over r, and that would be the limit 0 to pi okay. And h is what we call, and the notation we're going to use for h is it's going to be what's the letter we use? I think this is nu, or this weird v, I don't know. This symbol of f, and this is called the mean type. Okay. The mean type of f. So whenever you have a function bounded type, and then you have a mean type associated with it. What else? Yeah, so you can already see that this is really similar to the things we saw in problems 1 to 5, I guess. When just after the Fragment-Lindelof principle, we had things like this, but instead of log, we had the real part of the function. And the same thing here, we had log plus instead. And then we will see that indeed everything is related. So let me go to the proof. Proof. So for the proof, we will need some lemmas. So maybe I do the lemmas first. So we need a lemma, and again, following the numbers in the book, that would be lemma 4. So if f is analytic f bounded by 1 in the upper half plane and not identically 0, then define this number, capital H, as the lim inf, is that correct? Yes, the lim inf. the lim inf when r goes to infinity of 2 over pi 1 over r. So it's exactly the same thing, but instead of limit, we're taking the lim inf. Okay, then this is finite, which is the same to say, well, the f is less or equal than 1, so the log is going to be negative. So h is always a negative number. So saying that it's finite is basically just saying that's greater than minus infinity. And if I define this function here, so note when I define this function, maybe I should say first, then, and this guy is still less or equal to 1 in C+. Okay. So note that when I define this function here, this guy here, so I'm going to take the moduli, I will take only the real part of this, and the real part of this would be minus hy, but h is negative. So if h is not 0, it's strictly negative, then this is just like moduli of h times y, which means that this bit here is potentially greater than 1. Yet you still say that if you multiply by this thing, which is maybe greater than 1, the function still is, function times this factor still is less or equal than 1 in the upper half plane. Okay. So proof. Okay. So for this proof, there is a standard trick that we'll be doing over and over that I won't do anymore, and we'll just mention. Okay. So recall that whenever you want to do something and we don't know that the function is continuous at the real line, we do what I will call the epsilon trick. So we will assume, and we'll explain this epsilon trick in a moment. We assume f is continuous in the real line, okay? So it's continuous up to the real line. And if that's not the case, then we do the epsilon trick. So if, so otherwise, apply the epsilon going to 0 trick, which is you do everything we're going to do for the function fz plus I epsilon, where epsilon is something positive. And then you will conclude something for this function, and then you take epsilon to 0. Okay, so that should say use instead and take epsilon to 0. So a better name for the trick should be just the epsilon trick. Okay, of course that not every instance the epsilon trick will work. We have to see by the proof that clearly is going to work if we do it. We're not allowed to make promises that it's really complicated to check that it works. So if we make a promise whenever writing a proof, it should be clear, crystal clear that the trick is going to work to generalize the result. Okay, so let's see. So let's P be some positive guy, and then write Fp of z equals f of z e2 minus I pz. Okay, I want to send p to 0 in the end. So by the proof of the Fragment-Lindelof principle, which I guess was theorem 1, we have, recall that we deduce a certain inequality in there, assuming that a certain function was less or equal than 1, which is our case now. And the inequality was that log of Fp of z. Note that Fp is still less than 1 as long as p is greater or equal than 0. So this was less or equal than a squared minus z squared over 2 pi integral from 0 to pi for ay. Then we had the log plus here, p of ai theta sine theta. And then here we had ai theta minus z squared, and then ai minus theta minus z. So that's squared, yes, and then d theta. That was the inequality that we proved. Whenever I start with a function which is less or equal than 1 in the upper half plane, we had this inequality. Okay, and we actually then later put the f plus here anyway, but this is the one we deduced. Okay, so while I'm using this p, this little p here is just here now, so I can remove this plus here on the log. It's just a trick. So when I send p to 0, I can remove this thing. And then we'll have an inequality just for f, the same one, but just for f, and without the plus, the log. So now we have to use problem 25. It's also easy to show if you go through the proof of the Fragment-Lindelof principle again. So by problem 25, we have that y is always equal to a sine squared, and then the same squares here, which I'll just write it like this, dot, 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 square, which is exactly the same terms as the integral above. Okay, and this is basically just following by, first you prove it for a equals 1. Also this is, oh, and I should always say this is less than a, and that z in the upper half plane. Okay, and this also for the above formula. So for this one guy and this one guy, I had to ask this condition. Okay. And so this guy always follows by Poisson representation for the function z. Okay. Which also will follow for Poisson representation for the harmonic function y. Anyway, it's a simple problem to solve, and we have that. So that's good because what is on the left-hand side here is a term. So what is the left-hand side there? This guy here is equal to log of f of z plus, and then when you take the log of this other term here, what you get is p y only. Okay, but then y you can represent by this formula, which is incredibly similar to this one on the right, except that we have an extra a, we have an a squared, and we have an extra sign, we have a sine squared. Okay. So we deduce the following. We deduce that the log of f of z is less or equal than a squared minus 1 squared divided by 2 pi, then the integral from 0 to pi of a, and then here we have log plus of fp a I theta, and then we have a minus p a sine theta, close, and sine theta the theta, and then on the bottom we have the two squares. Okay, so far so good. And then you realize that this term here, so what is this guy? I would do in green. So what is this guy here? Okay, well, this guy there is what? Well, this is a log plus is just the log of f p of z, and then you take the max with 1, okay, and then you take a minus p a sine theta. Oh, this guy is a I theta, okay, but then this also can be split in two parts. This can be split in this plus, so let's increase here, and this is a, is this correct? Oh, there is a p as well, because there's a here and there's a p, so a p y, but y is a sine theta, so sine theta. Okay, so the maximum between this sum and 1, okay, but this is exactly the same term here, so I can add this minus term inside the maximum, so that the whole thing here will be equal to the max of the log of f of a I theta and minus pa sine theta. Okay, which is okay, but then I can take p to 0, and if I do p to 0, this will be less or equal than the max. Well, I have to take this term, so this will have to be just the log of f a I theta. Okay, any questions in this crazy computation here? Great, so I can erase everything. And just say that taking p to 0, we get that the log and then I have finished with the trick. We get this. Okay, great. Then now what we do? Well, then now is just, and this works for whenever z is less than a. Then we just take, so now what we do, we just take a to infinity. Yes, we take a to infinity, and by, so when we take a to infinity, you note that this right-hand side is fixed z, and you take a to infinity. There is an a here, and there's an a inside here. So in total, we have an a to the 4th on the denominator, and on the numerator, we have an a cubed. Okay, so result, we have just a 1 over a, and we have a y here, a 4 and a 2 pi. So then we take a to infinity, and we conclude that the log of f of z is less or equal than 2 pi, let's say y, and the lim sup when a goes to infinity of 1 over a. Then you remove everything here. And that would be exactly that, okay? So we conclude that, in particular, this lim sup is finite. Why is finite? Because, well, this is negative, okay? This whole thing, because f is less or equal than 1. So the worst case scenario, so this quantity is always less or equal than 0. Okay, but we just show that it's greater than something, which is not minus infinity. So therefore, this limit is finite, and it's what we called h. So this is h times y. Recall that that was the lemma, that this was the h. So we just showed that the h is indeed finite, and moreover, we just showed that this inequality holds, but this inequality is the same that saying that is exactly equivalent to saying this, because once you take the logs, you see that this inequality here is exactly as this one here. This one here. Okay, so that finishes the proof of the lemma. Any questions? Great, so where the epsilon argument goes, well, everything would work up to this point. Where? Up to this point here. You could have, instead of f, you could have f of z plus I epsilon. And then in this point, you could take epsilon to 0 and use Fatou's lemma to obtain the same inequality. This looks like it's in the reverse order of Fatou's lemma, but actually not, because this thing here is negative. Recall that f is always less or equal than 1. So you actually have to multiply everything by minus on both sides. And then you can apply Fatou's lemma and take epsilon to 0. And then when you take epsilon to 0, you will get the same inequality. So at this point, you could take epsilon to 0 and everything would work. Okay, so let's go to here. Let's go to the next lemma. I have 3 lemmas to prove the theorem. But then once we've proven these 3 lemmas, the theorem is almost direct. Lemma 5. What's lemma 5? Well, lemma 5 is basically the analogous one analytic, what? F less or equal to 1, F not identically 0, then if, again, capital H equals the lim sup when y goes to infinity of the log again, this is a negative, non-positive number, then h is indeed greater than minus infinity. So it's a finite number. And we still have that this thing is less or equal than 1, although this bit here could be greater or equal than 1. So again, a similar result. Proof. The proof here is a bit more tricky. But again, we can assume, but the same thing, we can assume f is continuous up to the real line. And we also can assume that h is strictly negative, because if it's not, then there is nothing to prove. And the same thing for the other one. Of course, that we can assume that f was strictly negative in the other one as well. Okay, so then take some negative number a between h and 0. Anyway, at this point, h could be minus infinity. I didn't show that it's finite. Okay, so if I take this guy, what we will conclude. Well, by the definition, we know that if I take the log and then if I take divide by y and take the limit in the imaginary axis, then we have this thing here. Since I'm taking the limit sup and a is something which is slightly larger than this limit sup, I do have the following. We do have what? We do have that f z. Oh, I'm not going to take a. Let me take b. Let me use this b instead. This will be bounded for some n positive. Well, because when you take the log, if I take the log, I'll have log. Oh, sorry, this would be bounded for z equals iy and y large. Okay. Yes. Is that what I want? Yes. Because, well, let's see. If I do this, if I take the log of these functions and divide by y, I will get a minus by. That's the function I'm going to get. Okay, so if I take the limit sup and this thing, I divided by y. So if I take the limit sup, this will converge to h. And so we have h minus b. And we know that this is strictly less than 0. If y is large, so therefore it's going to be, let's say, even less than 1 if you want, but just bounded, it's okay. Okay. Yeah, so I would take, so it would be less or equal than 1. So I would take m greater or equal than 1 here, just to help me out in the end. Okay. Okay. Now we're going to define an auxiliary function. Let's see. So let g of z be this guy, 1 over m f of square root of z e to I b square root of z. for z in the upper half plane. Okay, what's going on here now? So I'm taking, so this is a complex plane, and I'm taking the square root so that it sends the upper half plane into this quadrant here. Okay, so that's the square root I'm defining. So why I'm doing that? Because if I then evaluate, then I'm sending this line here, the imaginary axis, where we have a bound. Yeah, so recall that recall that f is by assumption bounded by 1, and this thing here is only going to explode at infinity. Okay, but I'm saying that at infinity is by assumption this is bounded. So therefore I can take this m, okay, and put here for m for y large, and for y is small between 0 and whatever, I can bound this by 1 and this by a number. So therefore I can take this bound, and this bound is going to work for, and then I can even like replace this guy here by every y greater or equal than 0. Okay, because at infinity is going to be bounded by a hypothesis and close to the, and for y is small or y bounded, this guy is bounded and this guy is also bounded. Okay, so I have a function which is bounded here by m, and I'm sending this thing to this. Okay, so it's going to be bounded now here. And that's why we're doing this trick. So G, well, the square root is still analytic in the upper half plane. So that's good. So this is still analytic. In C+. It still continues on the real line. Okay, because f is, and well, this exponential here is also. And what else? Well, and what happens in the real axis? Well, if I put x, then I will have 1 over m. Okay. So in the real axis, the square root of something in the real axis, this guy will still be real. Let me think. What happens with this guy? Well, definitely we're going to have this. Okay, and the function is bounded by 1, which is okay. And the other bit, let me see what the Branges says. The other bit, yes, the other bit is going to be bounded because what is the square root of a number? Yeah, I'm going to have I minus I and B. B is negative. Yeah, so the square root, the way I'm defining, and that's, I think that's the important point. The way I'm defining, if I do square root of minus 1 here, then what I'm going to get is I, okay, not minus I. So that means when I do I be at the square root of a negative x, let's say x is real and negative. So that is going to be what? That's going to be minus b square root of the moduli of x. Okay, which is going to be stat p it's going to be imaginary, and this guy, let me see if that's the way I'm defining. With I is minus I, then this is going to be, no, this has to be negative y. Is that? No, but I'm defining the square root of taking in there. Yeah, am I defining it the right way? Let's see. Maybe I'm doing a mistake here. So A is positive. So it has to be minus a positive number. It's a negative number, yes. So A is positive, that's going to be A X. Is there a problem here? Let's see. No, that's okay. I think my problem is, maybe you can help me out here. My problem is that I want to evaluate this thing on the real line. So we have something like this. Okay, and I would take the moduli of that. Okay, so if x is positive, that's okay, because this has moduli less or equal than 1, and f is less or equal than 1, and m is greater or equal than 1, so this function is going to be less or equal than 1. But if x is negative, then what is going on here? If x is negative, then if x is negative, then I will have, so this is for x positive. Okay, and if x is negative, I think I've solved the thing. Let's say if x is positive and I put the minus x here, so that's going to be 1 over m, and then f of minus x, which is going to be I square root of x, because it's going to be square root of minus x, which is I square root of x, and this is the same thing. It's going to be I b, and then I square root of x, which is going to be minus b square root of x. And then we have to take a look on what's going on here. So if I put z equals iy here, I get exactly iy in here and minus by in here. So if y was the square root of x, which is the thing I'm doing here, this bound is, this function is less or equal than n, okay? So since I'm dividing by m, since I'm dividing by m, then this is going to be less equal, everything is correct. Okay, so this works by this guy here. Okay. Okay. Any questions here? Got stuck a little bit, but now I think everything is good. Great. So we have a function g, which is bounded on the real line by 1. It's analytic in the upper half plane. And we do know that I want to apply the Fragment-Lindelof principle, of course. So let me go back to my notes. So we need a test. What was the test of the Fragment-Lindelof principle? I need to take a limit inf when r goes to infinity of 1 over r integral from 0 to pi of log plus of the g. That was the test, and I wanted this to be 0. Okay, but one can show that G of R EI theta, you can bound, well, F is bounded by 1, so this is just 1 over M. And then we have this bit here, which you just can bound by e to the moduli of the thing. Just put the moduli here inside. So it will be just b times r. So that would be e to the b r. Okay, just a moduli of b if you wish. B is negative, so let me put minus b. The worst bound you can come up with, okay? I don't care. Oh, not x. We have a square root there. So square root of x. Oops. Square root of r. And then great. Then you realize that the log of this thing is just O of square root of r. Which is okay. So that bit here will be O with square root of r, but you're dividing by r. Great. So this is 0. Okay, because of these estimates. Then I can apply the fragment Lindelof. The fragment Lindelof principle, G is less or equal than 1, which is the same to say, since I'm mapping everything here in this side, is the same to say that f of z e to I bz is less or equal to 1 if z is in the upper half plane intersection with x positive. Okay, then I apply the same construction, then do the same for the function f minus z bar, which is f star minus z. It's an analytic function. And we conclude that it's going to be bounded in the other, just a calculation to see that's true. If z is in the upper half plane and x is negative, conclusion, f of z e to I bz is less or equal to 1 in C plus. Is that? Oh, no, it's not less or equal to 1, of course. There was a 1 over m dividing. You're not paying attention, you didn't complain. This is m. Of course, because there is this m here being divided. So this is m. Of course. But then you realize, well, on the real line, this thing, so this is bounded, but on the real line is bounded by 1 because f is bounded by 1, and this has moduli 1 on the real line. So then you conclude that again by the fragment Lindelof principle that f of z e I b z is less or equal than 1 in C plus, because on the real line is bounded by 1. Okay, great. So then you just take b to decrease in the direction of h. If h was minus infinity, that would be a contradiction because f is non-zero. Okay, f is not identically 0, so I can't go to minus infinity and this inequality still being true. Okay, because f is non-zero. Again, recall that this thing is getting greater and greater and greater when you send b to minus infinity in the upper half plane. This thing is exploding. So it has to stop at some point. So therefore H is finite, and then I can put the H here and I conclude. Okay, any questions? Okay, we still have like 20 minutes. I think will be enough to finish. Okay, any questions in this calculation? I guess it got a little confused at some point, but now I think it's okay. And lemma 6 would be more like a reading exercise. Just state it and give an idea of the proof. Is if B is a Blaschke product, is a and BZ HIHZ is still less or equal than 1 for some H real, then this H has to be greater or equal than 0. Okay. And the proof, just an idea. The proof is to do by induction. So you define B of Z as, say, Bn of Z. Let me write it explicitly. It will be K greater than N. And then you have the Blaschke product. And then we have, let's say, K from 1 to N. Well, this would be K. Okay, so define this as Bn of Z times what else? Times the rest. Okay, and then show by induction that Bn of Z EIHC still is less or equal than 1 for every n. Okay, so you can one by one remove the factors and you still have something less or equal than 1. And the way you do it is, and you have to use here the epsilon trick plus the Fragment-Lindelof principle. And if you do that, you can use induction to show this. And you have to estimate these things here, these binomials, and the estimation. Take the moduli square, the estimation is something we already did. So you can estimate how large this can be. So you can apply the Fragment-Lindelof. Okay. So before we go to the proof, let's just observe that the lemmas show that, let me observe something, that the lemmas show that if you have a Blaschke product, then 0 equals the lim sup when y goes to infinity of the log y over I, and it is also 0. And this would be the actual limit. So the Blaschke product, well, it is of bounded type, of course, because it's bounded by 1 in the upper half plane. So it's bounded, so it's a bounded type. So you could ask the question, what is the mean type of the Blaschke product? Which is, what is the result when I take this limit or that limit? Okay, and the lemmas are showing that it's always zero. So you always have zero mean type. And so how can we show this? Well, it's simple. Let's say for the first one, so say I define H as this lim sup here. Let's say this guy. Okay. So since we know that it's bounded by 1, then lemma, it was lemma 5. Lemma 5 says that B, Z, E to I, H, Z, that this number is finite, by the way, and this thing is less or equal, still less or equal than 1. That's what lemma 5 shows. But, and this H has to be something less or equal than 0 because the Blaschik product is always less or equal than 1. But by lemma 6, H has to be greater or equal than 0. So therefore H is 0. And the same thing with the other limit. You just define as the lim, I guess in the other lemma was what? Lim inf. You just define H as the lim inf here of this quantity. And then lemma 4 will show that this thing is still bounded by 1. But then lemma 6 will show that H is 0. But then you show that the lim inf of this quantity is 0. But this quantity is always less or equal than 0. So therefore, the limit actually exists and it equals 0. Okay, so these are things easy to show. So maybe I should say, for instance. Okay, so now we can prove theorem 10. Before I prove it, let's just recall what's the statement. How much time I have? Still 12 minutes. That's theorem 10. So theorem 10 is just two formulas. Whenever we have a function of bounded type, no zeros accumulating at the origin, then you can compute this H here in the factorization, which is called the mean type of a function, as a limit in the imaginary axis or as an average limit on arcs. Okay. In the imaginary axis, we have to take the lim sup, but in here, it's actually the limit. Okay, so that's the statement. So let's prove that. So let's deal with the limit in the imaginary axis first. So F is B, Z, E, wait, wait just a minute. I think I wrote something wrong at some point. Yeah, the Branges always uses minus. Okay. Yeah, I know that was something. Is minus. I think in the way I wrote it put the plus. This minus H. Let me go back here and fix everything. This is supposed to be a minus. Of course, when you do this kind of thing, it has to be a minus, otherwise you're going to get, it's always minus IH times Z, so that this exponential grows at infinity if H is positive. So I have to fix in there. So probably I have to fix in another, yeah, in here as well. This is supposed to be a minus. And now this thing is going to be correct. This thing, let me see. G1 minus G2 with the minus is P1 minus P2. Yeah, now I think everything looks good. It's just a changing plus with the minus, but just to, these are the actual notes I put online and I want to be correct already. Great. So let me show, okay, and then we know that G has a certain representation. The real part of G is like y over pi, and then we have a measure mu. And this measure is not necessarily positive, but it's a difference of two non-decreasing. This function mu is a difference of two non-decreasing guys. Great. Bottom line, and if I take lim sup when y goes to infinity of the log y, well, this would be the same as taking the limit. I would take the real part here and divide by y and send y to infinity. So this bit here with y going to infinity, that's going to converge to 0, obviously. So this thing, this bit here is going to be just equal to h, which is going to come from this. That's why we need the minus, otherwise we would get minus h. And plus the thing with the Blasicki product, but we just showed that is 0 because the Blasicki product limit is 0. Okay, great. So part 1 follows easily. Let's do with the part 2. So, okay, if you do the other limit, which was to take the log and do an average over arcs, we know that the part for the Blasicki product goes away by the observation I did. This is supposed to be 2 over pi, 1 over r, integral from 0 to pi, log of f of r e I theta sine theta d theta. Great, the part for the Blasicki product goes away. We have an h, again, this limit, when you just put this guy, you just have an h. Because the integral of sine squared from 0 to pi is pi over 2. What else? And then we have plus the same thing for the g, okay? But then g, we know that g can be written as, let's say, you know that eg can be written as e2 minus u1 divided by e2 minus u2. And you have that the real part of u1 is greater or equal than 0. Okay, so then in here we have a limit which we're going to be something like it's going to be a limit. Let me just write it like this. Limit when, oh, this is not y, this is r. R goes to infinity of something, if the limit of this something exists. Okay, and I want to show that the limit of this something here exists and is 0. Okay, so how can we do that? This is actually simple. So, so let me define H, capital H, as the lim inf when r goes to infinity of 2 over pi 1 over r is the integral from 0 to pi of the log, the moduli of e to uj of r e minus I theta sine theta d theta. Great. So what do we know? Well, since the real parts of a greater or equal than 0, because by condition we know that these guys are less or equal than 1. This was problem 24. Okay, so then I can say that this indeed is finite, and this is by lemma So this is greater than minus infinity. And this is by lemma 4, we just showed, because we do have two functions that are bounded by 1. Great. And wherever we end by lemma 4, n minus uj plus ihjz, this still is bounded by 1 in C++. Okay, but then what that means is that if I take the log here and do the calculation, that means that 0 is greater or equal than the log of this guy. And this is going to be just y minus hj. Recall that hj is less or equal than 0, so this is a positive thing, greater or equal than 0. 1 over pi integral from minus infinity to infinity. Yes, I'm just taking the log of this inequality here above. And as isolating y. Okay. We know that this thing is negative for y positive. Then we are almost there because, well, this thing here I can rewrite, this thing is greater or equal than 0. Okay, so it means that this bit here is less or equal than 0. Okay, so it means that minus hj is less or equal, which is positive, by the way, is less or equal than 1 over pi integral from 0 to minus infinity, the sigma j t divided by t minus x squared. Okay, and then this goes to 0 if y goes to infinity, to plus infinity. So hj is 0. Okay, but then we showed that hj is 0, but hj was a lim inf of something which was always less or equal than 0. So therefore the limit exists, it's not only the lim inf, and the limit is 0. So to finish, thus the limit and this for each j, so I can already say that this is e to g is 0, and that's enough because that's exactly this bit here. Okay, so so then I can maybe say that okay, and that finishes the proof. Okay, any questions in this proof? Any other comments? Anything you want to add before I stop recording? Great, so thank you.